Alright, let's move on to the third part, the random sequence generator. Actually, there is already a component named a random generator in logisim, but as things goes, the random generator tends to output the numbers in with a bunch of ones stick together and a bunch of zeros stick together. So if you just use directly from the random generator to your asteroids input, it's not going to be look like asteroids. It's going to be look like a bunch of bots falling from skies instead. So we are going to add our own circuit, and the circuit is going to connect to the shift registers controlling the LED matrix, because that's the input, right? And you can design your own gates so that the random sequence generator is looking more random. And maybe if you want them to be more splitted apart, you don't want them to stick together, you can design your own gates. And actually the AND gate is a very simple and powerful tool, because a two input AND gate, it only output 25% of the time, because it has a total of 4 input states and only one is outputting high, and that's 25%. If you design your system with a 3 input AND gate, that's going to be an even lower 12.5% rate of it going high. So it depends on how you design your own circuitry here. So what I'm doing is that I'm using a 2 input AND gate. I'm going with the 25%. And you can try it out. If the 3 input AND gate works to your favor, if you want it to be like that, you can try. You can also try exclusive OR gates. You can also try not AND gates. A lot of combinations. It's very free here. It's just something you try to put together and see if the pattern looks like anything you like. Alright, since they are using the same input, you need something to toggle between the inputs, specifically one that can hold the output. What this means is that when you are displaying the game over scene, you want this input to be a constant input. You don't want it to toggle between different states. What I'm trying to say here is that if you are using the losing condition, where you crash, the losing condition is activated, and when you are not, the losing condition is not activated, right? So if you are using that to control your multiplexer, it's not going to work. Why? Because once you crash, it toggles here, right? It toggles to the game over scene. If you use just a simple counter here, it toggles to a game over scene. But then if you crash again during the game over scene, it's going to toggle back to the random sequence generator scene. And that's not what we wanted. We want the game over scene to completely run over what's designed, right? What's pre-recorded in the ROM. We want the message to be presented completely. So what we are trying to do is that we are trying to hold the signal here. Let's say signal 1 is going to the game over scene. We are going to try to hold it for a few clock pulses. Let's say 32 clock pulses. We're going to try to hold. So that requires a specialized circuitry, and that circuitry is a bit complicated. And when I look back, I have no idea how I thought that up. Right, we'll discuss that later in part 4. And yes, part 4 is here, the game over scene. This is the same input. I've said it a lot of time now. It's a bunch of fixed output, can be designed yourself. Use the ROM component in logisim, works with hex values. Take note, we work with hex values now. In this application, a special circuit was designed to work with this ROM so that the output can be finished completely. And this is what I'm trying to say earlier. We need to design a specialized circuit. So what's the thought process going to be is that the game over itself, for my design, is going to be 24 rows. You can design your own, which can be more, even more than 24. and you can just make simple adjustments on later when I show you the circuit. The period of inputting from ROM must be longer to make sure that the message is presented completely, and to make sure there is space between the end of your message and the start of the asteroids falling. So that's going to be longer than your message here, the length of your message. As I said before, the message is going to be from the top row. It's going to be going slowly downwards. Whatever you're trying to say in the message, it's going to be slowly downwards, and finally it's disappearing one row by one row in the last row of your display matrix, right? And in the middle of inputting game over, the condition of game over shall not be activated again. So this is some control condition. I say the condition of game over shall not be activated again. This is one of the methods of controlling the overall flow of the signal. You can also say that you want, instead of the condition not to be activated again, you can say that you lock the states of the flip-flop at that 32 clock pulses mentioned before. You lock the state of the flip-flop by using a special input. That also works. Depends on how do you want to design your circuit. What do I mean by lock is that this is a D flip-flop. D flip-flop is called a data or delay flip-flop for a reason. It's got a set here and a preset here. So what's going to change is that when you have set on high, it's going to be 1 no matter what the other inputs are. If you have preset at high, it's going to be 0 no matter what the other inputs are. So you can use this fact to hold the information here and not let it get changed by either clock pulses or the losing condition activated a lot of times. So you want to use this small piece of component here to lock your mux controller. This is going to control the bit select of your multiplexer. It's going to control the bit select here. The bit select decides whether to take from this input or this input. So it's going to here. It's going to control here. And yes, that's all. It's either 0 or 1 because we only have 2 inputs to choose from. This calls for a need of counter flip-flop and most importantly, control buffer. A control buffer looks like this. If you're drawing a symbol, this is the input, this is the output. When the input is 1, the output is not 1. Why? Because here is 0. But if here is 1, then only the output will be allowed to go through. This is a control buffer. So you control whether the signal goes through by turning this on or off. So this actually, if you think about it, is actually a transistor, a working principle of a transistor. You know how the transistor, let's say this is the collector, this is the emitter, and this is the base. If only there is a current here for a BJT type transistor, if only there is a current here, it will allow the current to go through here. It's actually a very similar, actually the same thing. Okay, that's what we need, a control buffer. So let's go over the details. First, the lose condition is activated, then the game over scene starts, and then the condition is kept until the game over finishes. You can adjust it to your own customized duration. For me, I want it to be 32 clock pulses, and my message length is 24 clock pulses. The clear score should be activated, so your score should be cleared upon the moment that you crash into the asteroid. And the condition finish, the ROM is not selected anymore, so we are going to have First, we are going to deselect the ROM. We are going to switch the marks to inputting asteroids, and we are going to set the ROM's address to 00. Because when we are outputting the ROM, it's going from 00 all the way to the 32 for me, all the way to the 32 address, and we want it to be back on the first address if we are going to show the game over again. So you want it to reset to that address again, and I will show you how to do that later. So basically what we need is a mod 32 counter, D flip-flops, actually not two, just one D flip-flops, a counter. A counter is actually a D flip-flop, but since I can't actually build any more circuitry over there, so I just use a counter. If you are interested, I make a video previously on counters explaining as much detail as I can. You can check it out. And then we need a ROM. ROM is written in all caps. We need a clock input. We need a loose condition input. We need a clear score output, which activates the circuitry so that your score is set to all zeros. And our mod 32 counter is like this. Mod 32. Alright, let's see. When it is all 1 here. 1 plus 2 plus 4 plus 8 plus 16. 31. Right? It's 31. And the moment that they all change to 0 and this is 1 here, is the 32, right? So the moment it changes here, the output is 1 here. So it goes and activate the reset input of every flip-flop. This reset input, once it's activated, every flip-flop is possibly turned to state 0, and it will start from 1. It will start from 0 to 31 again and reset on the 32 pulse, 30-second pulse. Then that is our mod 32 counter. Control counter, or I call this in my circuitry a control counter. This is not a formal name, this is just a name I give for this particular component in my circuit. So this control counter is only activated when the loose condition comes alive. And beware that during the 0 to 31, in this middle, if the loose condition arrives, we don't want the loose condition to reset the counter to 0 again. No, we are not going to do this. If that happens, the game over condition, the game over scene is not going to finish. So we don't want that to interfere with our counter. So the main problem here is that how do you keep the loose condition on until the game finishes? And that is to use a flip-flop, and not actually the loose condition to keep the loose condition on. You can adjust it to say that how do you keep the circuit on when the first loose condition is detected in the 32 clock pulse duration. So anything in between the 0 to 32 clock pulse duration, you don't want any other inputs. And we use a D flip-flop. I just discussed it. You got a set and a preset, right? The set is going to possibly set it to 1, a preset is going to possibly set it to 0. I think it's called preset. It's not called reset, it's called preset. Please correct me if I'm wrong. This output is used to control the mux, this Q output. And its output is going to also be controlling the counter of the ROM, the chip select of the ROM, and the mod 32 counter. So what it actually does is that, what I actually want to imply is that, you see there's a D flip-flop here. This is the D flip-flop. You see here, on a D flip-flop, its Q output its Q output is going to 4 places. One is the mux control, controls the either is 0 or 1 you want, and the ROM, if it is 1, the ROM is activated. If it's 0, the ROM is deactivated. And this is called a chip select. Chip select input. A chip select only activates if a chip select is activated, the ROM is accessible. If the chip select is not activated, the ROM is not accessible. If you don't connect any input here, the ROM still works. But if you connect input here and you display it to be at a logic level of 0, it's not going to be workable. And I want to mention a bit of a knowledge here. Let's say this is 0 volts, this is 5 volts. A typical FET gate field effect transistor or something like that. Let's say this is 4.5 volts, this is 0.1 volts, depends on the design. And this is called a logic level 0. This is called a logic level 1. And this is indeterminate. Indeterminate voltage from 0.1 to 4.5. What do we mean by logic 0 is that logic 0 there is still current, there is still voltage, there is still electricity, and there is still power. But the signal is interpreted as logical 0. It's not off at all. Like at one point of studying digital logic, you must has this confusion, like if this input is 0, this input is 1, does that mean no current here generates some current here? Well, that goes against the second law of thermodynamics, unfortunately. So what does it mean is that a logical 0 here means a logical 1 here. And you can see the logical 0 is a lower voltage, a logic 1 is a higher voltage, right? So actually in real life, a NOT gate, it actually comes from a IC. It's called a 7404 IC. That's what I named my channel after, because I really like this IC. This IC, it has a power input and a ground. It has 4 NOT gate inside. It has 4 NOT gate inside. So what it does is that this power input is connected to all 4 of these NOT gates. No, not 4. 6 NOT gates inside is the hex inverter. 6 NOT gate inside. And they are all connected to the power source and the ground. So what are you going to see is that it's something like this. If I remember correctly, this is a symbol for a transistor. You have the NPN type transistor. Of course, a NOT gate, also called an inverter, it can be implemented in many ways. You can use a transistor. You can use a transistor comes in a BJT, a bipolar junction transistor, or a FET, a field effect transistor. And there are different working principles. What I'm showing you here is a BJT, a bipolar junction. A bipolar junction meaning that you have 2 poles here, and PN, you have 2 poles. And what is it going to see is that this is the power in. This here is the power in. This is the ground. This is your input. This is your output. So this forms the NOT gate. So when your input is logical 0, meaning the current and voltage here is low. When the current and voltage is low, you know that when the base is low, there is almost no electricity going from the collector to the emitter, right? There is almost no electricity going in this direction. So all the current, all the voltage, it will go to this output. And this output will have a high voltage, right? So it's interpreted as logic 1. And if this is a logic 1, what is it going to see is that the current started flowing in this direction. And it is going to the ground. You know, the ground is a giant collection of charges. So whatever power in, let's say your power in is 5 volts, it's going to be around 0 volts here. So the potential difference is great. The potential difference is very great, and there are like almost no resistance. So the majority of the current is going here, majority of the voltage is going here, and this here it will be interpreted as logical 0 because it's on low voltage and low current. So this is how a BJT inverter works, a BJT not gate. Actually, just leave it here. A FET implemented NOT gate is much more. It's almost the same working principle, but it takes time to explain, so I'm not going to do it, and we are not going to babble about inverters. Alright, let's continue with the where have I just. Oh yes, chip select input. So your chip select input goes here, select the ROM. You want it to be high, we want to do things correct, we want to do things right. Of course, if you don't connect it here, it's also workable in this case, but we want to do things correct. Alright, and this is the second place it's connected to. The third place it's connected to is the counter from 0 to 31. And this is a NOT gate. Why do we want a NOT gate here? When 1, don't reset counter. That means that when this connection here is high, it means that we are currently displaying the game over scene. And if we are currently displaying the game over scene, we don't want to reset this counter. This is the reset input of this counter. So when we are 1, we don't want to reset the counter. When we are 0, we want to keep the counter as 0, right? So that the next time we can start at 0, 0 to 31. So when 0, reset the counter. So that's the reason for this NOT gate here. And this one here is the clock input. This one here is the losing condition input. The fourth place that this circuitry goes to is the control buffer of the mod 22 reset counter. What does it mean is that only when the lose condition activated this, and this is kept in high, right? It's kept in high. And only when this is turned high, this one here will be high, right? And only when this is high, the clock will be able to start the counting process on the mod 32 counter here. And ultimately, when 32 is reached, the reset condition will activate, right? And we use that reset condition to reset this flip-flop here to 0, and thus turning this to 0, this to 0, and disconnect this buffer. And when this is turned to 0, this is turned to 1, and reset this counter. So there's a circular connection here. So you see, it's a very interesting circuitry here. You have a circular connection. This is very interesting. I like this very much. So yes, that's how we control the input, which input we want to use. Let's move to the next point.